We talked a little bit about self-desiccation, but basically what we're trying to do is essentially figure out how do we calculate the amount of water that's in the system. So the simplest way to do this, if we want to just follow this rule of thumb, is we've got 7 pounds for every 100 pounds of cement in the system. A 6-bag mix is 564 pounds. 7 times 564 divided by 100 means we need 40 pounds of water. Right? If we've got an aggregate with 15% absorption, that's a New York aggregate. That's the magic number in New York. Right? Both suppliers. 40 pounds divided by 15% is 263 pounds of oven dry lightweight aggregate. So you got that 263 pounds of your lightweight aggregate. You got 40 pounds of water in the system. You're ready to go. Now you can go through other calculations now to figure out how you adjust your mixture proportions. I'm not going to go through these. If you really want to go through the math later, I'm happy to work through it. This isn't the method that I would suggest doing, although all the math works out and it's very simple and very straightforward. The real takeaway is at the end of the day, we have conventional concrete compared to internally cured concrete. Same amount of cement, same amount of water, same amount of coarse aggregate, same amount of air. The only difference is we've replaced a small volume of the sand with lightweight sand. Right? So all the hubbub that 308 has been going through is over this issue. Right? We're simply just taking out a small portion of sand and putting in sand that has little tiny holes in it that we hide water in. All right? Now, the next thing we'll do is we'll do a simple calculation on this where we sort of look at that supply and demand equation. If we look at the demand is really calculated based on 3 numbers. It's based on the cement factor, which is how much cementitious materials you have in the system, 564 pounds of cement, for example. It's based on the chemical shrinkage, right? This is that number we said that's about 7 ounces per 100 ounces or 7 pounds per 100 pounds, or we can go into milligrams if we want to. And then the maximum degree of hydration, and the simplest thing to say here is 100%. All right, so we do this calculation that says this is the demand of the overall system. Now, I've been saying 7. The actual technical average is 6.4. 6.4 and 7 in the field are the exact same number. Okay? The amount of lightweight aggregate, the mass of the lightweight aggregate times the porosity of the lightweight aggregate times the saturation factor. That's all it is. It's how much aggregate do you have, the porosity of the aggregate, and the saturation factor. So again, you could go through and you could rearrange that equation. You could calculate it out that you've got 560 pounds of cement. You've got the 0.07 chemical shrinkage. You've got 100 for your degree of saturation, porosity of 15%, degree of saturation of 1. All right, your aggregates are saturated, and you'll find out that that number is 262, which is really, really close to that 263. Right, so you get the same answer both ways. Right? Now, there's another approach that means you never have to take your calculator out of your pocket. All right, so this is an approach, and this is the approach that NIST was using, and Dale was mentioned earlier. It's a nomograph, and the nomograph essentially means that you can do this simply with these 3, and we can send out a plot later so that you can do this on your own. But you enter this plot knowing how much cement or cementitious material you have in the overall system. So again, 6-bag mix. You start here and you draw a line that goes straight up. And at this green line, that's a chemical shrinkage of 0.07, right? That same 7-pound number that we're talking about before. When you hit that green line, you take a left-hand turn, right? You go horizontally across, and you pick off, for your given water to cement ratio, you pick off the water demand, which here happens to be 39.2, all right, in terms of your water that's going to be inside of your system. You drop that down, all right, and you need 262 pounds of aggregate because each one of these lines corresponds to an aggregate with a different absorption rate. The green line is 15% absorption. So again, if you're trying to do quick calculations, this takes you, once you've done it once or twice, this takes you about 30 seconds with a ruler to just say, I start off with my cement, I go up to my chemical shrinkage, I come across to the water to cement ratio I'm using, drop down, and I know the amount of lightweight aggregate that I have in the overall system. Right? Now, there are lots of other more complicated things that we can add in, and believe it or not, there's about an hour of how to do the more complicated things on the ESCSI website. All right, there's a video. It's an hour of talking through how to do things like time dependence, or accounting for desorption, or accounting for other features than chemical shrinkage. So if you had drying that was taking place, you had something else that tells you how to do this. But as was mentioned a little bit earlier, almost nobody sits down with a blank piece of paper and says, let me design a mixture today. Right? Almost everybody sits down and says, I have a mixture that works, the DOT likes it, the contractor likes it, somebody else likes it. Let's figure out how we internally cure that. So the goal of this is to figure out how we go from an initial mix design into an internally cured mixture very quickly and very easily. Right? Now, much like the report that Jeff mentioned earlier, this worksheet that I will show you is worth every penny that you pay for it because it's free. Right? Just like that other report. Right? It's free. This is an Excel sheet that you'll get, or you can get. We'll send it out when we do the when we send out the PDF of the slides. But the Excel spreadsheet essentially has three main pieces. The first piece is essentially the piece at the top, and you'll see that there are these orange cells where you can add things in. These orange cells are where you would add in your target air content, where you'd add in your existing mix design, and your existing specific gravities. Right? So the only thing that we're doing in this design, in this part of the spreadsheet, is taking our existing mixture and putting it here. And if you said, boy, I have something else in my mixture, you know, we're from wherever and we do wild stuff in our mixture and we use 8 different types of aggregates, I'll redo the spreadsheet for you. Okay, or I'll send you one where you can edit all the things you want in the system. All right? The orange cells are what you get from your conventional concrete mixture that you're using every day. These are values that everybody should have, or should have a reasonable, good assumption for those values. The next thing you need to do is you need to add in 3 properties for your lightweight aggregate. All right, you need to add in the absorption, the desorption, and the specific gravity. Right? You enter those 3 properties, and if you get really close to the screen, this is green. And on the spreadsheet, it shows out that those are green cells. Now you may say, I have no idea what those values should be. The first thing you could do is I will give you a table that gives you those for, I believe, all the North American aggregates, at least that was accurate as of 6 years ago. And they're based on location, so even though everybody buys and sells a different plant every week, all right, the names of the plants haven't moved. All right, the other thing you can do is you can say, well, I can't use that table, I don't know where my aggregate's coming from. If you talk to your ready-mix supplier, you talk with the aggregate folks, they know these values for their particular materials. So again, if we've got a 15% absorption, very typical of New York, every single lightweight aggregate in North America has at least 85% desorption. That is the requirement to be an internally cured aggregate according to ASTM 1761. So if you don't know that number, plug in 85%. If you happen to be using a different type of aggregate that's not an expanded clay, shale, or slate, you may have to change that number. And for all of the expanded aggregates, it's 85% or better. And I would actually make the argument that it doesn't make a lot of difference if you're 85 or 87 or 88%. Go with the 85%, it's conservative, and just move on. So again, the basic idea, we've added in the original mixture, we've added in the lightweight properties, and then the spreadsheet automatically updates to give you your system. It essentially gives you the revised mixture design. So all of this is done within, depending upon what type of hamster you're using to run your laptop or your desktop, this is done in 3 to 10 seconds. All right, in a simple Excel spreadsheet, so you can start to play some of those games in the system. So the basic idea here is, right, we're essentially getting all of this information. We're going through the exact calculations that we were talking about before. That's the only thing that's happening in this spreadsheet. It's just going through the calculations that we've talked through, and it's science that's already been established to give you these new mixture proportions.